Class, in today's section we're going to talk about section 3.1, quadratic functions. And so, first we're going to remind ourselves what a quadratic equation looks like, and then extend that to a quadratic function. So a function of the form f of x equals ax squared plus bx plus c whenever a isn't 0 and b and c are real numbers is called a quadratic function. And whenever we talk about a quadratic function, we're often going to want to talk about standard form. So standard form of a quadratic function looks like this. F of x equals a times x minus h squared plus k. A still won't be 0. And then we're going to have special names for h and k. Because the point, h, k, is called the vertex. And so let me go on to a next slide and we'll unpack this standard form a little bit more. So we have slide 2, standard form. F of x equals a times x minus h squared plus k. And so we have some important characteristics. So we have hk is the vertex. We have that the graph is symmetric about x equals h. We know that if a is greater than 0, the parabola, that's the name we give the shape of this graph at right, and so that picture is just x squared. F of x equals x squared. So if we have something like 2x squared, it opens up. But if a is less than 0, so the parabola opens up, and if it's negative, the parabola opens down. So if instead of 2x squared we had negative 2x squared, and now we have a parabola that opens down. And so two related facts to this: if we have a is greater than 0, not only does our parabola open up, but our point f of h is a minimum, and if it's negative, f of h is a max. And so let me go to the next slide. So if we have f of x equals 2x squared, we can think of that as being 2 times x plus 0 squared plus 0. And so we said hk is our vertex. So our vertex is 0, 0. And because 2 is greater than 0, we know that it opens up. And that point f of 0, which in this case equals 0, is a minimum. And so just to kind of illustrate what happens as our a value changes, so we have our a value, and f of x equals ax squared. So let me go ahead and on this graph at the right, I'm going to graph x squared because that's our basic library function, which looks like this. I'm going to graph 2x squared, and then I'm going to graph 1/2 x squared. And so notice what happens here, and let me see if I can change the color of that color red. There we go. So I have these three graphs. H of x is that 1/2, g of x, the gray one, is 2x squared, and then f of x is just 2. So if I write that over here, if I have a equals 1/2, 1, or 2, they all open up. All have min at f of 0. But what we end up getting is this slightly flatter. So we have our basic function. Ooh, that's a rough picture. The half is flatter, and 2 is steeper, right? And so remembering our transformations we talked about a couple videos ago, here we have a stretch or a shrink. And it's easy to see over here on the graph on the right. And so this graph on the right is done in GeoGebra, which is a free app for both Android and iOS, but it's also available on GeoGebra's website or on your computer. So I highly recommend you download it, and in a couple videos we're actually going to use it quite substantially. But let me go ahead now, and I'm just going to reverse the sign. So instead of just a 1, we have a -1. A 2, we're going to have a -2. And in our half, we have -1/2. And so now I need to move this up, because what we end up seeing is they all open down. And instead now they have a minimum at that point. And so you're like, well, that's fine. That's what a graph looks like. These that make parabolas, but how do I actually do anything with them? So our first example is find the quadratic function of the form y equals ax squared passing through -3, -6. And so we know that it's going to look like y equals ax squared, which is our basic form for a quadratic. And we know that its x value, when it's -3, the y value is -6. So what we end up having is -6, our y value, is equal to a, whatever it is, times -3 squared. And so we have -6 equals a times -3 squared is +9, so we have a times 9. And a is -6/9. And now we can reduce that by taking a 3 out of both the numerator and the denominator, -2/3. And so that means our equation is y equals -2/3 x squared. And so whenever we're looking at a generic ax squared quadratic, it's relatively straightforward because all we need to do is find a. But what if we're working with standard form? So now we're looking at standard form, which remember means f of x equals a times x minus h squared plus k. And this question says find the quadratic function with vertex 2, 5 and passing through 3, 7. And so I'm going to go ahead and clear these graphs, because what I'm going to do is I'm going to graph this when we finish, and we'll see if what we get makes sense. So I'll hide that graph, and I'm going to move to the next slide so I have more room to work. So we know vertex is 2, 5, and a point is 3, 7. So our standard form is f of x equals a times x minus h plus k. Now, if you remember a couple slides ago, I said that vertex 2, 5 is our point h, k. And that's why we like standard form, because immediately we can see where the vertex of a parabola is based on this form. So we get a times x minus h is 2 plus k is 5. And now we don't know what a is, right? A is our unknown. But we know that when x is 3, y is 7. So let me write this as y equals a times x minus 2 plus 5. Well, if I substitute 7 for y equals a times 3 for x minus 2 plus 5. If I subtract that 5 over, I get 2 equals a times 3 times 2. 3 minus 2 is 1. So a is 2. That means our function, f of x, is 2x minus h, which h had a value. That value was 2. Ooh, that's an ugly 2. Plus k, which was 5. So we have 2x minus 2 plus 5. And so that means that we should have a parabola, because a is 2, that opens up. The vertex 2, 5, and it should, if all goes to plan, pass through 3, 7. So let's graph this function. 2 times x minus 2 squared. Oh, I dropped a squared. Oh man, I really dropped a squared. Well, that's unfortunate. No, it's not, because 3 minus 2 is 1, and 1 squared is 1. So, whew, we didn't lose much. 2x minus 2 squared plus 5. So let me zoom out and move that up. So notice that bottom point of that parabola is at 2, 5, which is exactly where our vertex we said was at the beginning. And then it also says that 3, 7 should be on the graph. So if I drag this over towards 3, oh, we're almost 3, 7. Whew. So that means this equation, f of x equals 2x minus 2 squared plus 5, is correct. So what if we weren't using GeoGebra? What would our process be? Well, so if we want to graph a quadratic in standard form. So let's first think of this as a series of transformations off our base function, which we'll call s of x, which is our squaring function. So then we can picture the first transformation as a horizontal shift. Because remember, our process is help students remember variables. So first we have a horizontal shift. And then we can apply another one, which is our shrink, or our stretch or shrink, x minus h squared. So we have a stretch or a shrink. And if that a is negative, we can also have a reflection. So that's our s and our r. And then, to get to our actual function, we have a times x minus h squared plus k, which is our vertical shift. And so I want to illustrate this with another example. And for this example, what we're going to look at is, let's go to my next slide, graph f of x equals 4x minus 3 squared minus 2. And I want us to think of this as a series of steps. So we have our x squared. So we have our squaring function, so we know that it starts like this. And then our h step, minus 3 means right 3. And so now we have something that looks like this. And then our stretch is times 4, so it's going to get a lot skinnier. And then we have our v step, which is up, not up, down 2. And so from this step we have over 2, but now we go down, and we have something that looks like that. And now let's see if we can get that to happen over here. So let's start with x squared. And then we'll go ahead and do x minus 3 squared. Shift to the right, 3. Then let's see if we can do our stretch. So we have 4x minus 3 squared. It got shrunk towards the middle. And then we have our shift. So we have 4x minus 3 squared minus 2. And that's exactly where we drew our shape. And so that's exactly the process we want to follow when we're graphing. We do our horizontal shift, and then we do our stretch or shrink, then we do a vertical shift, and then we have our final solution. And so let's look at graphing 2 more examples. And what I'll do for these is first I'll go ahead and delete these along the right, but I'm going to graph them by hand following the steps, and then I'm going to put it into GeoGebra to graph it and see if it looks like what we expect. So examples. F of x equals negative x squared plus 3. So first we have our library function, x squared. And then we have a reflect because of this minus 1. And so instead of opening up, it opens down. And then we have a v, a vertical shift, where we go up 3. So it should look something like that. So if our function is negative x squared plus 3, looks pretty spot on to me. And let's try another example. Here we have f of x equals negative 2, x plus 1 squared plus 3. And so our h, s, r, v. So we're going to go, this plus 1 means left 1, stretch times 2, reflect times negative 1. I'll use a dot instead of an x, so times 2, times negative 1, and v up 3. So if I start with our coordinate grid, we would start at 0, 0. If we had a normal parabola, we go left 1. We're going to stretch by 2, flip it upside down, and up 3. So we should have something like that. And if we're correct, we'll type that in over here. We go negative 2, parenthesis, x plus 1 squared plus 3. And that looks pretty good to me. And so graphing from our library functions is relatively straightforward whenever we have standard form. So graphing quadratics from the library function f of x equals x squared is straightforward when f of x, or let me change this f, we'll call that L of x for library function, is either ax squared or ax minus h squared plus k. Right, whenever we have an ax squared form or an a times x minus h squared plus k, it's relatively straightforward. But how do we go about doing something like this? Graph f of x equals x squared minus 2x plus 2. Because now it's not just a shift by a constant, it's essentially a shift by a linear function. And so what we need to do, and I'll give you the steps and then we'll come back to actually do this. So first we need to get the function in standard form, and we will always do that by completing the square. And so if I have x squared minus 2x plus 2, x squared minus 2x, I'm going to put this plus 2 over here just so I don't forget about it. To complete the square, x squared minus 2x, we take this middle term b, divided by 2, which is 1, and square it, which is 1. So here we need to add a 1. Because then what we'll be able to do is x minus 1 squared, FOIL that out, we get x squared minus x, which is negative 2x, minus 1 times minus 1 is 1. But we can't just add 1 to a function. That changes its value. But if we add 1 and subtract 1, right? So if we add 1 and subtract 1, that's the same as adding 0. So we're going to factor this piece, but then we need to combine this piece. So negative 1 plus 2 is 1. So I claim that my function here is the same as x minus 1 all squared plus 1. And now let's use GeoGebra to confirm that that is true. So GeoGebra, the nice thing is, we can just graph this as it was given to us. X squared minus 2x plus 2. And so that's the original. But now what if I graph x minus 1 squared plus 1? And notice that those two graphs coincide. I didn't mean to put that point there. Let's delete that. Right, and so for both of those, our graphs coincide. So that convinces us that it really is equivalent. And once we're in standard form, right, we certainly already graphed it, but once we're here, let me go to another slide. So step 2, identify A, H, and K. And so we had x minus 1 squared plus 1, x minus 1 squared plus 1. So A is 1, H is 1, and K is 1. So that means our vertex is 1, 1, which means if I put a point and I move it to 1, 1, it's just finicky because of rounding errors. 1, 1 is in fact there. And then we have that A is 1, so it should open up. And it does. So we identify A, H, and K. And then we have, the next step is if A is greater than 0, opens up. And A is less than 0, opens down. 4, we know our vertex is HK. 5, we can also find x-intercepts if there are any. So let me talk about x-intercepts with this example. Next slide. So an x-intercept means y equals 0. So if I have 0 equals x minus 1 squared plus 1, if I move this 1 over here, I get negative 1 equals x minus 1 squared. Well, no number squared equals negative 1. So there are no x-intercepts. But we can find y-intercepts, so that's our next step. Y-intercepts. So that's where x equals 0. So we have y equals 0 minus 1 squared plus 1. Negative 1 squared is 1 plus 1 is 2. And so that means we should have a point 0, 2 on our graph. If I drag this point over to x equals 0. Oh, there it is. Oh, it slid again. Let's see if I can manage to let go while I'm at 0, 2. So there was 0, 2. Ah, close enough. You saw that 0, 2 was there. And then sketch the graph. So you're like, well, what was that all about? Let me revisit those steps. So I have f of x equals x squared minus 2x plus 2. And I completed the square to say that was the same as x minus 1 squared plus 1. Well, that told me that hk was 1, 1, and a was 1. So that means I had a graph that if I went to the right 1 and up 1, there was my vertex. A was 1, meant it opened up, and then we found no x-intercept. That means it won't ever touch the x-axis. And we saw that the y-intercept was 0, 2. So that means my parabola specifically looks like that. And so this is just to give you a second way. So first we can start from our library functions. So we have 2 ways, and actually I'm going to say 3 ways to graph quadratics. The first is library function and standard form. The second way is that 7-step process, 7 steps with intercepts and vertex. And our third way is with GeoGebra. And so let me walk through one more example. If I have f of x equals negative 5 x squared minus 20x plus 13. And so we're going to need, so I'm going to follow my 6-step process, or my 7-step process rather, that involves me getting it in standard form first. And so this is, and remember our process for completing the square was that our coefficient of x squared had to be 1. So first, I know I'm going to want to work with these things, and the 13 is going to come along for the ride. So we have plus 13, but I'm going to pull a negative 5 out. X squared plus 4x. Because if I distribute that back through, I get my original back. And so what I need to do is take my middle term, let me pick a different color, middle term, divided by 2, and square it. 4 divided by 2 is 2, squared is 4. So I need to both add a 4 and subtract a 4. Remember, I need to add 0. Otherwise, I would change it if I just added 4. And so let me go back to my magenta. So I have negative 5x squared plus 4x plus 4 minus 4 plus 13. Well, that is negative 5. And if I just look at this piece, that's x plus 2 squared minus 4 plus 13. Well, I want to get these two numbers together. So let me distribute this through to both of these terms. I get negative 5, x plus 2 squared. Negative 5 times negative 4 is plus 20, plus 13. So I get negative 5, x plus 2 squared plus 33. And so first, we always want to go ahead and make sure that we do, in fact, have two equivalent functions. So my original was negative 5x squared minus 20x plus, nope, that's a divide, plus 13. Negative 5x, so we knew that a was negative, so it should open down. Let me go ahead and, I don't know what that is. Get rid of those two things. Is that believable? I would say it is, because it opens down, and my intercept, oh, I missed a number, didn't I? Plus 13. Negative 5, x squared, minus 20x, plus 13. And now remember, we don't know that 13 is our k value, right? Because it's not in standard form. So first, let's go ahead and compare it with our standard form. Negative 5, parenthesis, x plus 2 squared. Plus 33. And our two graphs do, in fact, coincide. See, if I turn off this blue one, you can see the green ones there, and if I turn off the green one, you see the blue one. And now we see that's pretty believable. We'll go ahead and, oh, I missed my graph. That point B looks like it should be at negative 233. Delete that. And so how did I know that that was negative 233? Well, that's because HK 233, A opens down, and negative 5 shrinks. And now this is an example where this one, so let me copy my function again, negative 5, x plus 2 squared plus 33. This has x-intercepts. Trying to write a 0 in there, but it's too close to the page back. So 0 equals negative 5, x plus 2 squared plus 33. Subtract that 33 over, negative 5, x plus 2 squared. Divide by negative 5. So negative 33 over negative 5 is what? Is 6 3/5. So it looks like 6 3/5. Let me confirm that with a calculator. Negative 33 divided by negative 5 is 6.6, which is in fact 6 3/5, x plus 2 squared. We can square root both sides, and we get 2.57 is about x plus 2, minus 2 from that. So x is about 0.57. And so that means if I drag this point, we should have 0.57, and we do. That is one of our zeros. And you might be like, well, where'd that other one come from? Because remember what happens when we add or subtract. No, when we take the square root, we get a plus or minus. And so when I add 2.57 to negative 2, so negative 2 plus or minus 2.57. Negative 2 plus that gives me this one, but then if I subtract, I get negative 4.57. Sorry, I wrote the wrong number there, but it was written up right above it. And so that means if I drag this point over here, when it's 0, it's negative 4.57. Spot on. So the thing I want you to take away from this lesson really is when we're graphing a quadratic function, which is either of the form ax squared or ax squared plus bx plus c, if we don't have ax squared form, we need to get it into standard form, because that standard form tells us how to apply our library functions to graph it. If you don't want to operate with the library function of x squared and applying your transformations, you can find hk, your vertex, use this if a is positive to see if it opens up, or if a is negative to see if it opens down. And then you can find the x-intercepts and mark them, and then sketch the graph. And while I want you to be able to do this by hand, I also want you to start exploring with GeoGebra and seeing if you're capable of graphing these functions, if for no other reason to check your work. Because as we move on to polynomial functions next, we're going to use GeoGebra more heavily. And that concludes section 3.1. Have a great day, everybody.